Okay, in this lesson, lesson number 3, we're going to look at geometric sequences. So the focus of this lesson, it says, is to provide and justify an example of a geometric sequence, derive a rule to determine the general term of a geometric sequence, and solve a problem that involves a geometric sequence. So we've looked at arithmetic sequences, which is where we have a sequence of numbers in which they have a common difference. Okay, arithmetic sequences have a common difference. And when we're looking at geometric sequence, they have a common, what we call, ratio. So what number are we multiplying 3 by to get 6 and then to get 12 and so on? So our common ratio here would be 12 divided by 6, which would be 2. So we take any term and we divide it by its previous term, and we can see that we get the difference of 2. Right, we can see it's 3 times 2 gives us 6, 6 times 2 gives us 12, and so on. This next one is not geometric, so we'll just not worry about that. That's plus 3, plus 5, right, plus 5, plus 7. Okay, what we want to do in this lesson, lesson 3, we want to look at geometric sequences. And when we're looking at those, we want to be able to provide and justify an example of a geometric sequence. We want to derive a rule to determine the general term of a geometric sequence. We want to be able to solve problems that involve geometric sequences. So if we look at the first example, it says exploring the pattern. What is a geometric sequence? So if we look at this first question here, if I look from 3 to 6 and 6 to 12 and 12 to 24, we have a jump in the numbers. But that would not be called a difference. A difference is, that refers to the common difference, that refers to the arithmetic, okay, common difference. When we're looking at a sequence that is geometric, we are looking at numbers that are being multiplied. So we call that a common ratio. Our common ratio, R, is equal to 2 here, okay? If we look at question B is not geometric because we're not multiplying by a common number. That would be times by 4. This would be times by something else. The pattern here, this is actually not geometric. Okay, there's definitely a formula here. These are all perfect squares. 1, 4, 9, 16, 25. The next one will be 36, 49, and so on. How are we getting that? Well, term 1 here would be 1 squared. Term 2 would be 2 squared. Term 3 would be 3 squared. So our general formula would be Tn would be n squared. Okay, the next one is geometric, to go from 8 to 4 and 4 to 2 and 2 to 1. We're getting smaller, so we're going to multiply those by numbers smaller than 1. Our ratio, therefore, would be 1/2. Right, half of 8 is 4 and half of 4 is 2. And another way to do that would be to take any term in my sequence, so for example 2, and divide it by the previous term, which would be 4. And 2 divided by 4 reduces to 1/2. Okay, that works with any term. So for example, if I took 1 and divided by the previous term, 2, we get 1/2. Or even 1/2 divided by 1, we'll get 1/2. So any term divided by its previous term. In a geometric sequence, a sequence in which it is a sequence in which the ratio of the consecutive terms is constant. So the ratio, okay, where in arithmetic it's a common difference, here it's a constant ratio. The common ratio or the constant ratio R can be found by taking any term except the first and dividing the term by the preceding term. So take any term, divide it by its previous term. That's what I did up here for C. So for example, if I took A up above here, if I took any term like 24, divided by its previous term 12, we get 2. There's our common ratio. Now where does this Tn and Tn minus 1 come from? If I look at these terms and I want to label them, or just number them, T1, T2, T3, and T4. If I take any term, so for example, term 24, that is T4, which is equal to 24, and divide it by its previous term, that's the same as saying T4 minus 1, which is saying take T4 and divide by T3, which is what we did. Okay, so take any term, divide it by its previous term. 4 minus 1 is therefore 3. Okay, that works for any geometric sequence. So determine the general term. To determine the general term of a geometric sequence, T1 is the first term and R is the common ratio. So if I have a term such, let's take the first one up above there. Let's say we have 3, 6, 12, and so on. If I look at my first term, for example, let's just pretend our first term is 3. Okay. We'll give a numeric example as well as kind of develop the formula here. Our term 2 would be our first term, T1 times by 2. So for example, over here, to go from term 1, which is 3, to get 6, we would take 3 and we times by 2, which gives us our second term. Term 3, I'm going to take 3 times by 2 times by 2 again, times 2 times 2, to get 12. And if we look at that in terms of sort of any number, a formula, a variable, we take our term 1 and we multiply it by 2 times 2. We multiply by our common ratio twice. To find term 4, we're going to multiply by 2 again. We would get 24. So to get from term 1 to term 4, we're multiplying by our ratio 3 times. Term 1 times 2 times 2 times 2. And as we move along, we can see there's a pattern. It's our first term times our common ratio to the power of n minus 1. So if I was looking here for my 8th term, for example, we would take our first term and we would multiply it by our common ratio 7 times. Okay, instead of there being 7 differences, we're multiplying by 7 common ratios. Okay, down here we did 3 times 2 times 2 times 2, which gives us 24. Our first term, T1, times 2 to the power of 3 is equal to 24, and that was our 1, 2, 3, 4, fourth term. Okay, term 1 times our ratio to the power of n minus 1. And that, of course, is our formula that we just sort of developed there. T1 is the first term, R is the common ratio, n is the number of terms, and Tn is the nth term, often known as the given term. Okay, sometimes we'll be given a term, or sometimes it's the last term, etc. Determine the first 4 terms of each geometric sequence. So if I look at this question, this example, we're looking at the first 4 terms we want. So I'm going to just write them 1, 2, 3, 4. And if we do that, our first term 1, term 2, term 3, and term 4. Our first term is, of course, 4. Our common ratio is 3. Times 3 is 12. Times 3 is 36. And times 3 is 108. If we try the second example, again, I'm just going to list out 4 little spaces here. No formula is necessary. Term 1, term 2, term 3, and term 4. Our first term is 3. Our ratio is -2. So if we want 3 times -2, we get a -6. Times by -2 is a +12. Times by -2 is a -24. So if you note, when there is a ratio that is negative, you're going to get alternating terms. Okay? If you get alternating terms, therefore, the ratio is less than 0. Our ratio is negative. Let's look at the next example. It says state the common ratio and find the next 2 terms of each sequence. So this first one, we see right away that it's plus, minus, plus, minus. I know our ratio is going to be negative. And to find my common ratio, I can take any 2 terms. -18 divided by 6 divided by the previous. -162 divided by 54. And 18 divided by 6 negative, I'm going to get -3. Or 162 divided by 54, we would get negative 3, either way. And now, of course, our next two terms, negative 162 times by 3, negative, will give us 486 positive times by 3 will give us a negative 1,458. Okay, for the next one, we've got this radical in there. So let's find the common ratio. I can take any term divided by its previous term. Our ratio here would be 5 root 3 divided by 5. And therefore, the 5's can cancel here. So our common ratio would be root 3. If I had come across and done my third term divided by second term, I would get 15 divided by 5 root 3. I could, of course, divide 15 by 3, or 15 by 5 rather, and get a 3. So I've then got 3 over root 3. But then if I rationalize both sides, both numerator and denominator, we get 3 root 3 over 3, which is, again, equal to root 3. No matter how you slice it, we get a ratio of root 3. Okay, and now I need the next two terms. So 15 times root 3 will be 15 root 3, and 15 root 3 times root 3 will be 15 times 3, which will be, 45. Okay, 15 times root 3 is 15 root 3. 15 root 3 times root 3 is the same as 15 times 3, which is 45. And there's our term 4 and term 5. Okay, and over here was term 4 and term 5. Okay, let's try the next one. Use the general term formula to determine the exact value of the indicated term. So if I want to look at this first one, my general term formula is Tn is T1 times r to the n minus 1. So we want our first term. We're going to multiply by r, right? Times r. But I want term 9. So to get term 2, again, I multiply by my ratio once. To get term 3, we multiply the ratio twice. So to get term 9, we're going to multiply that by ratio by the ratio 8 times. So term 9 is term 1, which is 2 rather, times my ratio, which is 5. 10 divided by 2, which is 5, to the power of 9 minus 1, which is 8, right? One last time. So T9 is 2 times 5 to the power of 8, which I believe should be 781,250. Okay. If we look at the next one, right away I see alternating signs. I know my ratio is going to be negative. So if I want to find that ratio, I'm going to take negative 1/6 and divide it by 1/3, which if I rewrite that, negative 1/6 times 3 over 1, we get negative 1/2. Okay. I could have seen this one quite easily as well, because 1 to 1, I'm timesing by 1, 3 to 2, 3 to 6, I'm timesing by 2. Okay, so we can see there our ratio is negative 1/2. And so if I want term 8, I'm going to take my first term, times by my ratio, negative 1/2, to the power of 8 minus 1. And I get a wonky decimal. And when I math fraction that, we should get negative 1 over 384. Okay. You can simplify this, or you can just put it all in at once. Okay, or put to the power of 7. Okay, but there's our T8. Okay, let's look at a problem-solving question. It says determine a particular term So sometimes you use a photocopier to create enlargements or reductions. Suppose an actual length of a photograph is 25 centimeters, and the smallest size that a photocopier can make is 67% of the original. Okay, so if it's keeping 67%, we could also reword this and we could say we're going to reduce, okay, we're reducing the picture length, okay, we're reducing the length by 33%. And if I think of that, like if I go to a store and I want to buy a shirt, say, and my shirt is on sale at 40% off, it's kind of like this is saying we're reducing this by 40%. But if I say I'm buying my shirt and I've got a 40% off sale, and my shirt is regularly $20, well, we can figure that out pretty quickly in our head. But if it was weird numbers, if that's the sale, sale of 40% off, then I know I'm paying, therefore I know I'm paying 60%. So I could do, instead of doing 20%, $20 times 40%, so 20 times 0.4, which would be 8, and then doing 20 minus 8, which is 12. Okay, that works. Another way of doing that is saying I'm paying 60%. Okay, that's 100 minus 40, which is 60%. So we're saying we're taking $20 and we're timesing by 0.6, which is again $12. Okay, but this is in one step. This one over here took me 2 steps. Okay, in this case, we are keeping, okay, we want to reduce the length by 33%, but we're actually keeping 67% of the original. So they could have also said, like I said, reduce by 33%. What amount are we keeping? This is going to be our multiplier. R is 0.67. So we start with 25. Okay, that's our original size, length. Our first reduction, I would take 25 and I would times by 0.67. And if I do that, I get 1675. And I times by 0.67. For my second reduction, if we times by 0.67, we get 11.22. Okay, nearest tenth of a centimeter. We'll round at the very end after 5 reductions. So if we notice here, we could keep going here, third, fourth, and fifth after my first reduction, and second reduction, and third. I'm just going to keep multiplying by 0.67. We get 7.51 or 2 times 0.67. I'm not deleting it out of my calculator. I'm just going to keep going. I get 5.04 times 0.67. And our final length is 3.375 or 3.4 centimeters rounded to the nearest tenth. So here's our final answer. Now, sometimes students say, well, what would be a formula for this? Well, we'd have to notice that our first term is actually the 25. So even though our first reduction is 16.75, our first term in this sequence, our T1 would be 25. Our first reduction is actually T2. Our second reduction would actually be T3. So if we're looking at after 5 reductions, that would actually be T6. So T6 would be T1, which would be 25, times your ratio, which would be 0.67 to the power of 5. And if we plug that into our calculator, we will get the exact same thing of 3.4 centimeters. Okay? Okay, so for the next example, if you can figure out it says, suppose you purchase a house for $380,000 and it appreciates by 3% per year. What will be the value of the house after 25 years? So if we start with that house after 1 year, 380,000. Okay, that's our start amount. Okay. And this second term will be after 1 year. And if I multiply 380,000 times 1.03, right, because what this comes from is our house is appreciating in value by 3%. So we have 100% of the house plus it gains 3%, which is 103%. So our decimal will be 1.03. That's our ratio. And if we multiply 380,000 times 1.03, we get 391,400. If we multiply that by 1.03, we get 403,142. And that's after 2 years. After 2 years, which would be term 3. And so if I want after 25 years, therefore that's going to be term 26. So T26 will be our first term, 380,000 times by 1.03 to the power of 25. And if we plug that in for term 26, we get 795,635.6, which I guess to the nearest dollar would be $795,636. Okay. Let's look at the next question. Example number 5. It says, in a geometric sequence, the third term is 54, and the sixth term is negative 1,458. So I'm going to write 1. I can make little spaces, just kind of fill in the blanks. 1, 2, 3, 4, 5, 6. And my first term, I don't know. I know my second term. I don't know my second term, rather. I know my third term is 54. And my sixth term is negative 1,458. Right away, I know my ratio is negative because it looks like even numbers, even terms are negative and odd terms are positive. So they're going to alternate. How do I figure this out? What I want to do, again, is I want to say it's kind of like when we make a common difference created formula, but instead I know from 54 to term 4, and from term 4 to term 5, and from term 5 to term 6, we're multiplying by our ratio 3 times. So 54 times r cubed is equal to negative 1,458. So if we divide both sides by 54, r cubed therefore is 27 negative, and therefore our ratio is the cube root of negative 27, which is negative 3. There's our ratio, and if we go backwards therefore and divide by negative 3, I get negative 18, and divide by negative 3. Going backwards, we get a positive 6. So there's our first 3 terms. How about you try the next question? Okay, give the video a pause and give it a try. So for this example, I got a ratio of 4. When I went through and solved and created my own equation, 28 times r cubed is 1792. And then I was able to find my ratio of 4 and list my first 3 terms. Okay, we'll save this question for the classroom or for tomorrow's lesson. If I look at the assignment, I would recommend that you did questions 1 to 5, the odd letters, and numbers 6, 8, and 9. If I look at the assignment, I just want to do one question together quickly. Lesson 3. Let's do 3 B together. So if I'm looking at question 3b, it says simply determine the number of terms in each geometric sequence. So if I want the number of terms, I can use my Tn formula, which is T1 times R to the n minus 1. So 640 would be my Tn. My T1 is, of course, 5 root 2. And my ratio, well, our ratio here, if we do 10 divided by 5 root 2, we get 2 over root 2, which is 2 root 2 over 2, which simplifies to root 2. So our ratio is root 2, and that's to the power of n minus 1. What I can do here is we can divide out the 5 from both sides, and 640 divided by 5 should be 128, which is equal to root 2 times root 2 to the power of n minus 1. So in Math 10, we do have a strategy using logarithms, but in Math 30 rather, we have a strategy using logarithms. But in Math 20, we haven't learned those yet. So what we would do in Math 20 is we would just use a guess and test strategy by creating common bases. So what I want to do here is write everything with a common base of 2. So 128, I know, is 2 to the power of 7. Square root of 2 is 2 to the power of 1/2. And square root of 2 to the n minus 1 is 2 to the 1/2 to the n minus 1. So I'm just going to rewrite those. That's 2 to the power of 7, which is equal to 2 to the 1/2 times 2 to the 1/2 to the power of n minus 1. Now this second 2 to the 1/2 to the n minus 1, that's my power of a power law. So I'm just going to squinch this over here, okay, rewrite this over here, and what we get is we get 2 to the power of 7 is equal to 2 to the 1/2 times 2 to the 1/2 n minus 1/2. Right, this 1/2 distributes to both terms outside of the bracket there. And now I know on the right-hand side here, when I multiply two powers to the same base, we add the exponents. So our left-hand side remains 2 to the 7. Our right-hand side is going to be 2 to the power of 1/2 plus 1/2 n minus 1/2. The two 1/2s, positive and negative, those cancel. So we end up here with 2 to the power of 7 is 2 to the power of 1/2 n, or 2 to the power of 7 is 2 to the power of n over 2. So therefore 7 is equal to n over 2, and therefore n is equal to 14. So it simply says determine the number of terms in each sequence. 640 is term 14. If you have any other questions or concerns, please do not hesitate to contact me. Thank you.